Understanding quarks, the building blocks of matter. Have you ever wondered what the universe is really made of? At its core, everything, from the air we breathe to the stars in the sky to the cells in your body, is built from incredibly tiny particles. And today, we're diving into the mysterious world of quarks, the fundamental building blocks of matter. Most of us know that atoms are made up of protons, neutrons, and electrons. Did you know that protons and neutrons themselves are made up of even smaller particles? The quarks. Quarks are elementary particles, meaning they can't be broken down into anything smaller. They combine in specific ways to form protons and neutrons, which, in turn, make up the nuclei of atoms. Interestingly, quarks are never found alone. They are always bound together in groups due to a phenomenon called color confinement. We will explain that shortly. Quarks are of 6 types or flavors, which differ from one another in their mass and charge characteristics: up, down, charm, strange, top, and bottom. Quark properties. Charge. Quarks carry a fractional electric charge. Up, charm and strange quarks have a charge of +2/3e. And down, strange and bottom quarks have a charge of -1/3e. For example, a proton has 2 up quarks and 1 down quark, adding up to a total charge of +1. Spin. Quarks have a property called spin, which describes their angular momentum. The spin of each quark is 1/2, which means they are Fermions arbitrary particles having half-integer spin. Mass. Quarks have varying masses, the top quark being the heaviest. The up and down quarks are the lightest and the most stable. They make up protons and neutrons, which form the atoms in everything you see around you. The charm and strange quarks are heavier and rarer, found in high-energy environments like cosmic rays or particle accelerators. And then we have the heavyweights, top and bottom quarks. The top quark, discovered in 1995, is the heaviest of them all. Quarks have a unique property called color charge. But don't let the name fool you. It has nothing to do with visible colors like red, green, or blue. Instead, color is a fundamental characteristic that governs how quarks interacts through the strong nuclear force. There are 3 types of color charges: red, green, blue. Quarks combine in such a way that their colors cancel out, forming a color-neutral particle. For example, a proton or neutron contains 3 quarks, 1 red, 1 green, and 1 blue, creating a balanced color-neutral particle. A meson, which is a quark-antiquark pair, achieves neutrality by pairing a quark with a color, e.g. red, and an antiquark with the corresponding anti-color, e.g. anti-red. The strong nuclear force, mediated by particles called gluons, ensures quarks remain bound together. Gluons are like tiny messengers that carry color charge between quarks, constantly swapping colors to maintain balance and stability. This brings us to an important concept: color confinement. Quarks are never found alone because of their color charge. If you try to pull quarks apart, the strong force between them doesn't weaken like gravity or electromagnetism. Instead, it becomes so powerful that the energy creates a new quark-antiquark pair, keeping quarks bound in groups. This ensures that particles like protons and neutrons remain stable and intact. Quarks combine to form particles called hadrons. The most common hadrons are protons, made of 2 up quarks and 1 down quark. Neutrons, made of 2 down quarks and 1 up quark. Protons and neutrons then form the nucleus of atoms. These atoms make up everything around us, including the cells in your body. Studying quarks help us unlock the secrets of the universe. For example, particle accelerators like the Large Hadron Collider smash particles together at high speeds, revealing quarks and their behavior. In medicine, particle physics is used in technologies like PET scans to detect diseases. Quarks also existed freely in the first moments after the Big Bang, helping us understand the universe's origin. Now that we know about quarks, let's meet their counterparts. Anti-quarks. Anti-quarks are the antimatter version of quarks. Anti-up, anti-down, anti-charm, anti-strange, anti-top and anti-bottom represented by the same letters with a bar on top of the letter. Just like quarks, anti-quarks are never found alone due to colour confinement. Instead, they combine with quarks to form particles called mesons. For example, a pion is made of one up quark and one anti-down quark. Antiquarks are just like quarks, but have opposite properties. Opposite electric charge. While an up quark has a charge of plus 2/3. An anti-up quark has a charge of -2/3. Opposite colour charge, which is related to the strong nuclear force. Anti-red are anti-green, anti-blue. Other quantum numbers are also reversed. Antiquarks are not commonly found in everyday matter. However, they do exist in high-energy environments such as particle collisions, cosmic rays, and radioactive decay. Antiquarks are a crucial part of understanding antimatter, which plays a significant role in modern physics. Here is a question for you. If a proton is made of 2 up quarks and 1 down quark, what would an antiproton be made of? An antproton would be made of 2 anti-up quarks and an anti-down quark. Let's summarise. Quarks are the fundamental building blocks of matter. There are 6 flavours of quarks, but up and down quarks are the most common. Quarks have a property called colour charge, which governs how they interact via the strong nuclear force. Now here's a question for you. If a neutron is made of 2 down quarks and 1 up quark, what is its total charge? Think about it and comment below. From forming atoms to helping us understand cosmic events, these tiny particles connect us to the mysteries of existence. If you enjoyed this journey into the world of quarks, don't forget to like, share and subscribe. Stay curious and we'll see you in the next video. Thank you.